Today we want to continue finding the interval of convergence for a power series. This has two components, identifying the center and then identifying the radius around that center. The interval of convergence for a power series always has something in the middle. We always get convergence at the center of the series. And then we get convergence in some radius around the center. A plus R and A minus R. When we plug in the center of the series, we zero out almost all the terms. All the non-constant terms get zeroed out, and that's why we get convergence. So we always get convergence at the center of the series. And the coefficients will determine how much radius we get around the center. And because this is a radius, this is what we get above and below. That's how a radius works. So the center is just given by the form, and then the radius will be determined by the coefficients. The other thing that we have to check are the endpoints. Oh, I wanted to say the radius is determined by the coefficients. And we also want to note that the radius could be 0 and the radius can be infinite. The radius can be 0, positive infinite, or infinite. So our three possibilities of the radius being 0, positive infinite, or infinite. The other thing we have to check individually are the endpoints of the interval of convergence. So we also have to consider what's going on at the endpoints. So the endpoints can be in or out of our interval of convergence. These are the four possibilities that we were talking about once we had a finite positive interval of radius of convergence. I could have the interval from A minus R to A plus R. A minus R could be included while A plus R is not included, or the other way around. A minus R is not included, but A plus R is included, or both endpoints could be included. Point is, the endpoints have to be checked individually, because what's going on at the endpoints is that the ratio is saying the limit is 1. And so the ratio test doesn't know what's going on at the endpoints. The way that we're going to determine this is based on reading the factors in our general term for the power series. This is our base model. I have the simplest coefficient. Here, Cn is equal to 1 for all n. The first thing that we want to notice is that this power series looks geometric in x. So this most basic power series is geometric in x. There's a common ratio of x. And so our interval of convergence is the absolute value of x needs to be strictly less than 1. That's exactly when a geometric series converges. That's what the ratio test would say is happening. When we check the endpoints, if we plug in 1, we get a series of 1s, which diverges. If we plug in -1, we get an alternating 1 minus 1 plus 1 minus 1, which also diverges. So neither of those has a sum. So the endpoints are not included. So I could list this interval of convergence with interval notation. I'm saying we go from, oops, not included, and then everyone will be included, right? We could list this interval of the convergence in interval notation from -1 to 1, but the endpoints are not included. So now we want to start messing with this basically. The easiest thing to deal with is moving the center back and forth. That just makes a horizontal shift of our whole function. So if I have the series as n goes from 0 to infinity of x minus 2 to the n. So now all the terms are 1, and then x minus 2, and then x minus 2 squared, and so on. So in this case, the coefficients are still all 1. The coefficient part is still 1. So from our previous example, the radius of convergence doesn't change. Up here, the radius of convergence was equal to 1. And our interval of convergence was everything within 1 unit of 0, which is the center of the series. The center of the series here, x minus 2 to the n. The center is going to be at 2. So that's where we get convergence. 2 is what zeroes out all those terms. That's the middle of our interval of convergence. Since I didn't do anything to the coefficients, the radius of convergence doesn't change. So our interval of convergence will be the absolute value of x minus 2 has to be less than 1. Or if we graph it, in the middle is going to be 2, 2 plus 1 is 3, 2 minus 1 is 1. So here is our interval, a graph of our interval of convergence. We'll say from 1 to 3 in interval notation. We can see that the endpoints are going to be invisible. What's going on at the endpoints will be invisible to the ratio test. But if we plug in the endpoints, when x is equal to 3, the series is a series of 1s. We get the sum of 3 minus 2 to the n, or the sum of 1, which diverges. When x is equal to 1, we get the sum of 1 minus 2 to the n, which is a sum of -1 to the n's, which diverges. Both of those series diverge because the limit of the terms is not 0. Notice that the endpoints, 3 and -1, we get the same two series, 1 to the n and -1 to the n, that we did in the previous example, because all we've done for this second example is shift over to z. One thing that we want to make sure we notice is that the center is what makes the terms 0. So if I have another series that says x plus 3 to the n, the form that we want to read is x minus a. So what we have here is x minus a -3. Think about what makes the terms 0, because that's where we always get convergence. So if I draw a graph of our interval of convergence here, in the middle, I'm going to put -3. And since my coefficient is still just 1, I'm just going to have my base radius of convergence of 1. So it goes up to -2 and down to -4. Or in interval notation, -4 to -2. So we can cope with wherever the center happens to be. That just changes the middle. And if we don't do anything with the coefficients, we don't change anything about the coefficients, then we're just going to have our radius of convergence of 1. Our interval of convergence is defined entirely by the value of x. Just the coefficient with just 1, it doesn't matter. Coefficients don't care. The ratio test is going to focus on that exponential factor, x plus 3 to the n. Polynomial in x, exponential in n. Let's start playing with that exponential in n part. Let's start playing with a positive finite radius of convergence. Exponential factors, this is exponential in n, that will change the positive finite radius. The base version of this is our positive finite radius is 1. That's why we're only getting convergence based on the value of x. If we want to adjust that, so here I have an exponential factor in n. I'm dividing, my coefficient is 1/5 to the n. This is going to produce a factor of 1/5 in the limit from the ratio test. So the limit from the ratio test is going to be the absolute value of x plus 3 to the n over 5. So the limit from the ratio test, after we go through that, what's going to fall out of there is an absolute x plus 3 over 5. To make an interval of convergence, solve for the absolute value parts. So we're going to multiply by 5. For our interval of convergence. So if we solve for the absolute value factor, that will get us the interval of convergence. This absolute value inequality says everything within 5 units of -3. If we draw a -3 at the center and go 5 up and down, that's everything within 5 units of -3. We always get convergence at the center because that will zero out all the terms. If x equals -3, then this becomes a sum of zeros. We have to check the endpoints. Since we're dealing with the ratio test and there's no rational or radical factors, we're not going to get anything at the endpoints. So we have to check in the ratio test. So we check them individually. So if we look at -8, when x equals -8, our series is -8 plus 3 to the n over 5 to the n, or a -5 to the n over 5 to the n, or just -1 to the n, which diverges. The power series diverges when x equals -. At 2, we're going to get the non-alternating version of this. When x is equal to 2, we get the sum of 2 plus 3 to the n over 5 to the n, or the sum of 5 to the n over 5 to the n, which is just a sum of ones, which diverges. So our interval of convergence is from -8 to 2, not including the endpoints. Notice that when our general term from the power series had a 5 to the n in the denominator, that showed up as the radius of convergence. It was, in fact, the limit from the ratio test was a reciprocal of the radius of convergence. So if I take that 5 to the n and move it into the numerator, we should expect a radius of convergence of 1/5. So our coefficients just look like 5 to the n. If we didn't have that x plus 3 to the n, we would just say that this is just a series, this divergent, because geometric with a common ratio greater than 1, and we know that divergent. But the other factors being raised to the n, x plus 3, that has variables. So based on the value of x, if I plug in the right values of x, that will make our common ratio less than 1. So this is geometric, our common ratio, or the limit from the ratio test, will end up being, once we do a ratio test, our limit will come out 5 times the absolute value of x plus 3. Since this came from a ratio test, this limit has to be less than 1 to get absolute convergence. And to write an interval of convergence, we solve for the absolute value factor. So this is everything within 1/5 of a unit of -3. So we're going to have -3 in the middle. And we're going to go down to -3 and 1/5. And up to -3 and -1/5. In this case, the endpoints, just like in the previous example, the endpoints will not be included. The endpoints will produce a series of 1 to the n and -1 to the n. So this will produce the series 1 to the n, which diverges, and this endpoint will produce the series -1 to the n, which also diverges, just like in the previous example. We are changing exponential stuff and running it through the ratio test. The ratio test does not know what's going on at the endpoints. So we check individually, and we get 1 to the n and a -1 to the n at the endpoint. If you want to see some examples where the endpoints get included in the interval of convergence, we need rational or radical factors in our coefficient. It's rational and radical factors that will allow endpoints into the interval of convergence. I'm going to keep the 5 at the end, but move it back down to the denominator. So my radius of convergence can be 5. But now I want to include some endpoints. So also in that denominator, I'm going to include some rational or radical stuff. I'm going to say drop an n squared. With the n squared in the denominator, here are the things that we read based on these factors. This is the goal. -3 in the middle, radius of 5, endpoint of -8 and +2. Both of those endpoints are going to be included because the coefficient at the endpoints the coefficient part is going to give us a 1 over n squared and a negative 1 to the n over n squared. So we'll get a 1 over n squared on one side and an alternating 1 over n squared on the other side. Both of those are convergent. Both the endpoints are going to be included. The ratio test ignores this n squared. So these are the things that we observe. Centers at -3. This 5 to the n factor tells me that the radius is going to be 5 because the 5 to the n is in the denominator. This n squared is going to tell us about the endpoints. That n squared is going to be ignored by the ratio test, but it's going to be relevant to the endpoints. Let's do a ratio test. We'll take the limits as n goes to infinity of the absolute value of an plus 1 over n plus 1 squared times 5 to the n plus 1. And then we'll multiply by the reciprocal of an. Then we do the cancel palooza. We have x plus 3 to the n plus 1 over x plus 3 to the n. That will leave an absolute value of x plus 3. Five to the n over 5 to the n plus 1 will leave a 5 to the 1 in the denominator. And then we'll also have an n squared over n squared plus 1. So as n goes to infinity, all the factors that came from the rational factor in the ratio test, that all goes to 1. So we're left with absolute x plus 3 over 5. This is the same limit from the ratio test we had in the previous example, where we didn't have the n squared. So the ratio test just ignored that n squared business and just said, nah, I only care about the absolute x plus 3 over 5. So the limit from the ratio test is absolute x plus 3 over 5. And we get convergence in the ratio test if this limit is less than 1. So there's the ratio test, ignoring the rational or radical factors, and thus not knowing what's going on at the endpoints. So our base interval of convergence is absolute x plus 3 is less than 5. Because as usual, we solve for the absolute value factor to write our base interval of convergence. The difference here is because of that n squared, we get a different series when we plug in the endpoints. In the center, we've got this -3. At the bottom end, we've got a -8, and at the top end, we've got a 2. We need to know what's going on at -8 and 2. In the previous example, where we didn't have the n squared, we saw that the x plus 3 to the n over 5 to the n canceled out either to a 1 to the n or a -1 to the n. But now I've got that n squared. So now when x is equal to -8, our series looks like -8 plus 3 to the n over n squared times 5 to the n. So we get this -1 to the n over skip a step. So a lot of the same things are happening. -8 plus 3 gives us a -5 to the n over an n squared times 5 to the n. And just like before, the 5's cancel, and we get a -1 to the n, but this time with an n squared. And this is absolutely convergent. The alternating is not important. 1 over n squared convergent, with or without the alternating. This means that the power series converges when x equals -8. So -8 is included in the interval of convergence. So up here, -8 is included in the interval of convergence. Then the same thing is going to happen at 2. When we plug in the 2, we're going to get a series that looks like 1 over n squared, which is also absolutely convergent. So when x is equal to 2, we get the series 2 plus 3 to the n over n squared times 5 to the n. We get the series 5 to the n over n squared 5 to the n. The same thing with the n 5 to the n happens. Cancels out to a 1, but we're still left with an n squared, which is still absolutely convergent. So the power series converges when x equals 2. So 2 is included in the interval of convergence. So up here, I'm going to draw a square bracket for 2, so I want 2 to be included in the interval of convergence. So now our interval of convergence includes what's going on at the endpoints. So in interval notation, I would write it in square brackets. Because both endpoints are included, I could also modify my absolute value inequality to say x plus 3 less than or equal to 5. Now, this does look like an awful lot of writing, but this is an awful lot of writing that's going to take place in your mind. This is writing that's not going to take place on the paper, and therefore it's not going to take time, at least a few days. We're going to look at the form of general term of our power series and know immediately that the center is going to be at -3. We're going to have a radius of 5, and both endpoints will be included because of the n squared. And if we start making adjustments to this, we'll be able to come up with the same read. So for example, if I change everything, let's suppose that I put a 2 to the n in the numerator and have an x minus 5 to the n out here. And in the denominator, I'm going to put a cube root of n for, I don't know when that would come up, but There it is. Here are the things that we observe. The center is going to be at -5. We always get convergence there. We never look at a power series and say this thing diverges, because it always converges if we nuke all the terms. We always have that nuclear option. So we've got 5 in the center. And I'm going to have some radius above and below. I look at the other exponential factor, that 2 to the n. It's in the numerator. So it looks like our radius of convergence is going to be 1/2. So we're going to go up to 5.5 and down to 4.5. I did throw a wrench at this one. I have a cube root of n in the denominator. This is going to converge on one end. So remember the endpoint, for the endpoints, ignore the exponential stuff that's going on. The endpoints are going to be a 1 over cube root of n, which diverges, and alternating 1 over cube root of n, which converges conditionally. If we plug in 5.5, that's going to make this factor a 1/2 to the n, and these cancel out. So the series at this end, when we plug in the endpoints, will be the series 1 over cube root of n, which diverges. It's a p series with p equal to 1/3. But at the other end, when we plug in 4.5, we subtract 5, we get -1/2 to the n. That multiplies with 2 to the n to leave a -1 to the n. So the series on this end will be the alternating cube root of n, which is conditionally convergent. That means we're going to include 4.5 and exclude 5.5. So our interval of convergence will include 4.5 where we have conditional convergence and exclude 5.5 where the series diverges. Four and a half, yes, because the conditional convergence. 5.5, no. Absolute convergence everywhere in the middle. The thing that we didn't bring up today, which is the thing that we'll bring up tomorrow, is how do we get to a 0 or an infinite radius of convergence? You'll notice that none of these examples include factorials. And what do factorials have something to do with? Factorials have everything to do with it. Factorials are going to, factorial factors in the general term of our power series could produce a radius of convergence of 0 or a radius of convergence of infinity. That is, we might only get convergence at the center, or we might get convergence everywhere. All right, we'll look at some of those examples tomorrow, along with some more examples of this exponential and rational radical stuff. That's it for today. I'll see y'all on tomorrow, but have a good day, and thanks for playing.